All right, I think we're online and sorry I was late because I had some other engagements this morning. So thank you for being here. Okay, before the start of the class. All right. So here we are going to continue from where we left off in the last discussion here. So this is our discussion on Laplace transform. And this is part 3 of Laplace transform. All right. So again, just to recall what we have studied already. So we have, rather, in the very first discussion on Laplace transform, we described Laplace transform as an extension of Fourier transform, and as an extension as such that we can calculate the Laplace transform for signals for which the Fourier transforms do not exist, because those signals were not absolutely integrable, right? And after that, we did calculate the Laplace transform of a few popular signals, and we figured out that whenever we are discussing non-causal signals and we are considering bilateral Laplace transform, we are supposed to provide the region of convergence, the condition on S, condition imposed on S, under which the Laplace transform actually converges, under which the Laplace transform actually exists. And we figured out that if you are talking about the generalized bilateral Laplace transform, in that case, just talking about the Laplace transform of a signal is not sufficient. We do need to provide additional details like the ROC, right? Otherwise, the things won't make any sense. With that said, we also simplified the things a bit, and we said that in control system engineering, for the most part, we discuss only about causal systems and causal signals, right? And what are causal systems? Causal systems are those systems for which the output at any given instance can be calculated by knowing the present and the past inputs. And there is another definition of causal system. From this, you can actually derive that for a causal system, the impulse response of the causal system is also a causal signal. Now, what is a causal signal? A causal signal is a signal for which the value of the signal is 0 before time is 0. So basically, for negative values of time t, the value of the causal signals would be equal to 0. And also, if I have a causal system, namely a system whose impulse response is causal, and if we excite the system with a causal signal, so if the input is also causal, then the output is proven to be causal. And from that, we actually figured out that if we have causal systems and causal signals, if you're only talking about everything causal, under that scenario, we figured out that we do not really need to talk about bilateral Laplace transform, and we do not really need to talk about the region of convergence, because there will be a complete one-to-one correspondence between the Laplace transform and the inverse Laplace transform. So we figured those things out, right? So here, again, I told you the formal definition is the bilateral Laplace transform, but we often use the unilateral Laplace transform because we are talking about causal signals, right? And since causal signals only exist, rather only have a non-zero value after t is equal to 0, then doing the integration for the entire range from -infinity to infinity over t, that's not really required. So from that, we actually use the unilateral Laplace transform. So in any case, if xt is a signal, then the Laplace transform of the signal is defined as this integral. This is the bilateral Laplace transform. All right. So where S is the complex frequency denoted by sigma plus j omega. It would have a real part and an imaginary part, right? And if xt is causal, that is, xt has a value of 0 for all t less than 0. So as long as t is less than 0, if the value of the signal is 0, then actually this can be rewritten as, we are just writing what we actually did in our last discussion. This can be rewritten as this, of course. So the integration can be from -infinity to 0 xt e to the power minus st dt and plus 0 to infinity and xt e to the power minus st. And since for a causal signal or a causal system or something like that, this would be true that the value of the signal would be 0 as long as time is negative. So this value would be 0, right? So this part will not be there. So our definition of Laplace transform would essentially turn out to be this, right? And also we won't need to really discuss the right. And also we won't really need to discuss the region of convergence because we won't have any non-causal signal as the uh, inverse Laplace transform, right? So this is our famous unilateral Laplace transform. Right. So this is what this is the definition that we are actually going to use for deriving our Laplace transform expressions for the most part, and for deriving any condition or any rather any property of Laplace transform, we are probably going to use the full definition, right? All right. So this is sort of as far as this one is concerned, this is something we have studied in the last class, right? We have studied in the last class, right? So let's start our discussion with one calculation, right? So let's consider another example. Okay, just like our previous class. So we did quite a few Laplace transform, and now let's continue our discussion, right? Let's continue with a very simple signal, which is the unit ramp signal. Again, ramp signals are pretty important. Okay, someone is asking, can we use unilateral Laplace transform everywhere? Okay, as long as you are not dealing with non-causal systems or non-causal signals, you can use unilateral Laplace transform without any issue. As long as you are not dealing with non-causal systems or non-causal signals, right? As long as everything in your system is causal, fine, you can use the unilateral Laplace transform. Okay, so rather let me write it down. As long as the systems and the signals are causal, we can use this one, right, instead of the bilateral Laplace transform. So that would be true, right? All right, so now let's calculate the Laplace transform of our famous ramp signal, written as RT often, right? Again, what is RT? Let me just draw it. Okay, RT is essentially TUT. RT is essentially TUT. So it will be like a straight line with unit slope passing through the origin, but only difference would be this multiplication with UT. This multiplication with UT would indicate that the value of the signal would be 0 before time t was equal to 0. So if this is t and this is RT, then this is what the ramp signal actually looks like. All right, so these are the unit slope, this is the unit ramp, right? So if I write 2 RT, in that case there will be 2 TUT, so the slope would be 2 and as such, right? So that's fine, right? And again, we proved in our earlier class that this signal is again does not have absolute integrability, right? So it does not have is not absolutely integrable. So if you just do the integration like this, minus infinity to infinity, take a mod on this RT dt, this will actually diverge to infinity, because as time increases here, the area under this curve actually goes on increasing, right? But since we can suitably multiply it with something, and with that we can actually figure out a proper Laplace transform. The Laplace transform would actually exist. So we actually did show that the Laplace transform of this signal actually exists by choosing a suitable value of sigma. So choosing a suitable value of the real part of S. So by definition, I can use this definition. Okay, but again, for that I have to split it between two parts, and again you can see as long as t is negative, the value of the signal is 0. So I can just make the lower limit 0 at the onset, right? So this is rt e to the power minus st dt. That would be the Laplace transform, right? So of course, what is rt? Rt is tut, and ut has served its purpose. And what was its purpose? To make the lower limit turn to 0, right? Instead of being minus infinity. And what is the value of r? That's r, right? So I can just say 0 to infinity, it's just r, and sorry, it's just t, and then I have e to the power minus st dt. That's fantastic. And with that, I can now do this integration as a normal human being, okay, like normal people do. We can do it in using integration by parts. I'm showing you how actually you can do this using integration by parts. Of course, we are going to consider the first function to be this one. So we only consider those functions to be the first function for which the derivative is very easily found, and for which by calculating the derivative you're kind of reducing the order. And this will be the second function, okay, easily integrable. So this is the integration by parts. So you are writing this. So 0 to infinity minus integration 0 to infinity. But I'm going to show you a better way of doing this kind of integrations, right? I'm going to show you a better way. Anyway, so this is going to be again a derivative of this. So a ddt of t, and then an integration from integration on e to the power minus st dt, and then a dt. That's a very simple one, right? So that's going to be, again, if you just do a simplification, that's going to be minus 1 by s, okay, and that would be a constant, and then I would have t e to the power minus st, and then I would have limits like 0 to infinity, and 0 to infinity, that's a 1, and I would have 1 by s once again for the integration, and from that I would have e to the power minus st dt. All right, so I would have minus 1 by s. I'm not putting the limits just yet, okay, I'm not putting the limits just yet. Again, this 1 by s is going outside simply because of the fact that that's irrespective of t, because the limit is for t here. All right, and again, if I do this, this becomes minus 1 by s square, because I have another 1 by s going out, and this becomes e to the power minus st 0 to infinity. All right, so with that said, I can now combine this whole thing into a single limit, if I say so, or rather let's just put the values here. Let's simplify this a bit. Okay, so this is, now we actually discussed this on our first discussion on Laplace transform. So this is this one, right? So this is like 0 to infinity minus 1 by s square, and I'm also writing this this way so that things are like easily understandable, right? Now if I put the upper limit, here, see, try to understand what happens if I put the upper limit. If I put the upper limit here, then on the numerator I have infinity, but on the denominator I have a bigger infinity. But do I always have a bigger infinity? I have to ensure that in the denominator I have a bigger infinity. Then only I can ensure that the limit is 0, right? On the upper on the numerator I have an infinity, right? If I put t equal to infinity, t tending to infinity. But on the denominator I have to ensure that e to the power st is a bigger infinity. Okay, how can I ensure that? I can ensure that by just assuming that the real part of this one is positive, just like that. Okay, if the real part of s is positive, then I can ensure that this actually goes to positive infinity, because limit s, we did this in our last discussion, right? So limit s tends to infinity, e to the power st, if I have that, okay, that actually goes to infinity if the real part of s is greater than 0, right? So we have that just like that. So again, so that is sigma essentially. So under that condition, this is going to be converging. So the upper limit would be 0, because I have infinity on the numerator, but in the denominator I have even a larger infinity per se, right? Like e to the power infinity, e to the power positive infinity, sort of. And if I put 0 as the lower limit, then in the denominator I would have 1, but in the numerator I would have 0. So that way, that's also a 0. Minus, then I have 1 by s square, right? And So now if I put infinity here in the new the upper limit here, based on the same discussion here, I would have 0 as the lower limit, and then if I put 0 here, I would have 1 as the lower limit, right? So that will be 1 by 1. So the answer is 1 by s square. So that would be pretty simple, like not a very difficult thing to understand, right? I believe it's pretty simple, right? So under this condition only this happens, right? So we are going to say that the Laplace transform, that is, we have just realized that the Laplace transform of RT, which is essentially TUT, okay, is equal to 1 by s square, provided that the region of convergence is given by this, provided that I'm assuming the value of sigma to be positive. So this is basically sigma. So those are the conditions. This is not strictly necessary to write, but I'm writing to show you that these are there. Okay, these do not unconditionally converge. Okay, that the result do not unconditionally converge. So that's the Laplace transform of this signal, right? So not a very difficult thing to understand, right? Now let's generalize this and let's calculate another example. Let's calculate the Laplace transform of t to the power n ut. Okay, let's generalize this and calculate the Laplace transform of t to the power n ut, where n is supposedly some integer value, right? Some positive integer, right? Could be, what should I write? Zalen greater than equal to 6. So what it means is that so n is essentially 0, 1, 2, 3, things like that. All right. All right. So if I am calculating this now, again, if you have any query during the discussion, feel free to ask. All right. And again, for the most part in this in today's lecture, we are going to work out a few examples, and then at the end we are going to derive a very important important expression that will be there throughout our entire course, right? So, and if we are now integrating this, of course, by definition here we are going to do the integration from 0 to infinity, simply because of this ut, right? So ut has actually served its purpose by reducing the limit to 0, right? So that will be like that into e to the power minus st at, right? All right, and as such we could approach this problem by doing n number of n number of integration by parts, right? I would have to reduce it once, then again and again and again, but there is a better way of doing it. What better way? We could treat this as a gamma function. So, and again, somehow gamma function came up in one of our earlier discussions on signals and systems. How is gamma function defined? We know that gamma function, for example, gamma n is defined as this improper integral. So e to the power minus x and x to the power n minus 1 dx, like that. And instead of x you could write t, it won't matter, right? So this was our definition for gamma function, right? So the point, so let me just write t instead. All right, fine, x will be fine, right? So that's our definition of gamma function, right? That's called gamma n. All right, so we are going to use the definition of gamma function here to actually calculate the result here. All right, so I'm kind of assuming a little bit of first year mathematics. All right, so now we have to reduce this as just like e to the power minus t, something like that. I have to make this e to the power minus x, right? This term has to match up with this term, right? It has to be e to the power minus x. So what am I going to assume? I'm going to assume st to be equal to x. Okay, this is our assumption. So let us consider st to be equal to x, where s is a constant here. Okay, and with that this will be s dt equal to dx, right? And subsequently dt would turn out to be 1 by s dx, right? 1 by s dx. And what about the limits? So I'm writing t here and I'm writing x here. So t had original limit from 0 to infinity. So t was originally 0 and then it was infinity. So if again, if t is 0, then what about x? X is 0. And if t is 0, then what about x? And if t is infinity, what about x? x is positive infinity, but here is the condition. Here is the condition. Try to understand. We have this st equal to x, right? We are saying that t is infinity, a very large quantity, right? Of course, with that said, if s has a positive real part, under that condition, the result will be positive infinity. If it has a negative real part, then the result will be negative infinity. So here lies the condition. We are again assuming that the real part of s is greater than 0. So here lies the condition. Otherwise, the integration won't converge. It won't even be a gamma function. Got it? Right? If s is negative, something like a negative quantity, and what is a negative quantity? So we are assuming real part to be negative. Under that case, this would be negative infinity. So nothing would work. So, and again, with that said, again, what is t? And t is essentially x by s. So what is t to the power n? T to the power n is essentially x by s whole to the power n, and that's x to the power n by s to the power n. Recall n and s are irrespective of the integration. So basically, with respect to the integrations variable, they are constants. So I'm integrating again from 0 to infinity because these are the modified limits. And for t to the power n, I'm writing x to the power n by s to the power n. And here I'm writing e to the power minus x because st is equal to x. And what about dt? dt is replaced by 1 by s and dx, right? And s, this entirety of x is s is a constant. So s to the power n multiplied by s, so which is s to the power n plus 1. This thing is entirely a constant, so it can go outside the integration and live happily there. And we have this in the denominator there. And this integration is now from 0 to infinity. So we have now e to the power minus x and x to the power n dx, right? Now look at the very definition of gamma function. The very definition of gamma function tells me that if I want to put, for example, 2 here, I would have to put 2 minus 1 here, right? So this will be essentially 1 here. So this is gamma 2, right? Similarly, if I put 5 here, so if I want to calculate gamma 5, that would be integration from 0 to infinity on e to the power minus x 5 minus 1 dx, right? That is going to be x to the power 4, just like that. So obviously, since I have, look at this integration here again. So if I have n here, that indicates that I'm essentially calculating the gamma function for n plus 1, right? So just like that, this is 1 by s to the power n plus 1 gamma n plus 1, right? All right, and it can be proved, which I have to skip at this point. Okay, it can be proved that gamma n plus 1 is essentially n gamma n. All right, gamma n plus 1 is gamma n plus n gamma n, and that can be actually seen very easily from this. You can just do integration by parts once and you would end up with this result. And from that I can say n gamma n is, for gamma n can be written as n minus 1 gamma n minus 1, and gamma n minus 1 can be written as n minus 2 gamma n minus 2, and so on. Essentially what would happen is it will end up being n into n minus 1 into n minus 2 and so on up to gamma 1. And what is gamma 1? Gamma 1 is, can be calculated to be 1, because gamma 1 is essentially integration of e to the power minus x dx from 0 to infinity. That's equal to 1. So essentially what I have is n into n minus 1 into n minus 2 up to 1. So that's nothing but n factorial. Okay, but this happens only if n is an integer. Otherwise we cannot write something like a factorial. So this is going to be n factorial divided by s to the power n plus 1 if n is a integer, positive integer, or equal to 0. So this condition, essentially, if this condition is satisfied. All right, so we have this. So we can actually, what we have derived is that the Laplace transform of t to the power n ut, okay, in general is n factorial divided by x to the power n plus 1. So as a simplification, if we put n equal to 1, then we have Laplace transform of t ut, which is the unit ramp signal. So that will be 1 factorial divided by s to the power 2. And what is 1 factorial? That's 1, and that's s square. So this is something we just derived a moments ago, right? So that actually checks out. But what is the condition? The condition lies here. That's the condition. This condition must be satisfied. Otherwise, this won't even be integrable like that. Are you getting the point? Many of you have already left. Fantastic. Maybe I should just consider that you people know everything and skip everything over. All right. So my request is that if you don't understand something, please ask. Okay. Maybe some of you don't feel like attending classes, right? And that's not an issue. Anyway. All right. Okay. So again, if you have any query, feel free to ask. So one propeller signal. So now we have now essentially calculated the Laplace transform of signals for which the Fourier transform do not exist in a proper sense, right? Now let's calculate the Laplace transform of something for which the Fourier transform actually exists, right? This is a signal for which the Fourier transform actually exists properly, right? And this is also absolutely, I mean, not necessarily properly absolutely integrable, but yeah, the Fourier transform for this actually properly exists without any issue, right? In terms of delta, in any case. All right. Now, of course, you have to use certain tricks to actually calculate this. Let's see. So let's define this. So we are starting from 0 to infinity, or not this one. I have to write multiply ut. So essentially, once again, this signal looks something like this. This is a sinusoid, but this is a causal sinusoid. What is a causal sinusoid? A causal sinusoid, again, the same thing like a sinusoid, but when time is less than 0, the signal has a value of 0. And why did that happen? Because of this product multiplication with ut, right? So this is called a causal sinusoid. So this is t, and this is here it is sine at ut. Of course, at will determine the frequency of this. All right. So with that said, let's do the integration here. So I have sine at. I have to multiply it with e to the power minus st and write dt here. Wow. Now we have a problem, right? So we have to do integration by parts, and then we have to go through we have to do integration by parts twice and go through certain shenanigans to actually do this integration, right? Instead we could use Euler's formula, which is e to the power j theta is cos theta plus j sin theta, and similarly e to the power minus j theta is cos theta minus j sin theta. Okay, adding these two would give me e to the power j theta plus e to the power minus j theta, and that would be 2 cosine theta. So essentially 2 cosine theta would be e to the power j theta plus e to the power minus j theta by 2, and subtracting these two equations would give me e to the power minus j theta, sorry, e to the power j theta minus e to the power minus j theta, and that's going to be 2j sin theta. You people know this already, right? And divide everything by 2j, you have sin theta equal to e to the power j theta minus e to the power minus j theta divided by 2j. Yes, absolutely. Someone is asking, question is, are we multiplying ut just to make it causal? Yes, you are absolutely correct. We multiply with ut just to show that the signal is causal, just to make sure that the signal has a value of 0 before time t is equal to 0, right? As long as time t is negative, the value of the signal is 0. So just to make the signals causal, we multiply everything with ut. Okay, so in order to make a signal causal, right? That's kind of the one of the primary purposes of UT, and that is one of the primary purposes for which Heaviside himself used the Heaviside theta function, so namely the unit step function. So now we are going to, instead of doing the integration by part shenanigans here, we are going to use this. We are going to use this definition here, okay, of sine theta. So essentially, for sine AT, I am going to write this as integration from 0 to infinity. I have e to the power JAT minus e to the power minus JAT by 2j into e to the power minus ST dt. Notice that this e to the power JAT and e to the power minus JAT, they are essentially sinusoids. They do not have any real parts there, like, right? So e to the power JAT, this entire exponent is complex, right? E to the power minus JAT, this entire exponent is complex. But for this part, e to the power minus ST, for this part, this S has a real part and an imaginary part, right? Just keep that in mind. Don't forget that. And in any case, this 1 by 2j can happily go outside because that's an outsider. So that's a constant, right? So integration like that. So I would have e to the power JAT minus e to the power minus JAT, and I have to make these smaller. All right, and we have multiplied with e to the power minus ST dt. All right, so let me just do the multiplication, inner multiplication properly. So do the integration, right? So, before doing the integration, so I have e to the power minus ST there, and we have e to the power JAT like that. So what I'm doing, so of course multiplication with this will actually result into a sum of the exponents, right? Sum of whatever appears in the power. So I would have minus ST plus JAT in the numerator, in the exponent here in the power. And here, of course, I can factor out t, so I can take t common out of this entire thing. And I'm going to also take the minus sign common out of this entire thing. Okay. So with that, this is going to be e to the power minus S minus JA t. And then with a minus sign, I would have e to the power. Now, of course, the same thing, it is going to be S plus JA t. Again, oh, sure. Someone is saying yes. Yeah, that's why it's called rough work, right? Fantastic, thank you. So you people are actually following it, right? All right, so right, this is 1 by 2j. Now, of course, it's time for the integration, right? So again, this is going to be e to the power minus S minus JAT, and this entire thing will go to the denominator of this thing, and we would have e to the power minus S plus JAT divided by minus S plus JA, and the lower limit would be 0, upper limit would be infinity, right? Of course, this is a constant as far as this one goes, right? And now here we are going to see something interesting here. Okay, something interesting here. So now let's think about the limits here. I'm going to talk about the limits here. So let's think about the limit of one of these quantities, right? So let's think about the limit, because we are going to put the limit in any case, right? We are going to put the infinity limit here on there, and we cannot just say by putting infinity I'm getting a 0. It doesn't happen that way, right? Okay, so let's think about the limit. Let's think what happens if I put infinity as the upper limit here, right? So let's consider the first expression here. So what if I put limit t tending to infinity on this expression, e to the power minus S minus JAT? Okay, you cannot just say this is equal to 0 without saying anything, right? Mathematics is not that easy, right? So of course, and let's expand this a bit. Say let again limit t tending to infinity. So what is S? S is sigma plus j omega, and then with that I have minus JA and t like that. Sorry, where is the exponent? Where did the e go? Here is the e, right? All right. So here now I can now combine these two complex imaginary terms here. So limit t tending to infinity, e to the power minus. So I would have sigma plus j omega minus a, and then a t like that, right? And now I can expand this term, rather write this in this way. So that's going to be limit t tending to infinity. I would have e to the power minus sigma t multiplied with e to the power minus j omega minus a t, right? We just expanded the power in the exponential, right? So again, e to the power minus sigma t, that's a real decaying or increasing exponential, and here this is going to be cos omega minus a into t minus j sine omega minus a into t. So again, the same point stands as the previous examples. This is going to vary between minus, so this is going to, again, just like the previous in the last day's class, this is going to vary, this value is going to vary in a square about the origin in the complex plane, right? This value is never going to be larger than going to be outside this, right? So this is 1 plus 1j, so this can, and this is minus 1 plus 1j, this is minus 1 minus 1j, and this is 1 minus 1j. So this is not going to go beyond this, so this value will lie, so this is finite as far as I am concerned. So this is finite, okay? Only this term can decay and become 0. What is the condition under which this term decays and becomes 0? Okay, so this term will become 0 if sigma is a positive number, right? Again, sigma is a real number, right? If sigma is a positive real number, then this term would become 0, right? So with that said, this is equal to 0, so 0 multiplied by a finite quantity, that is 0, if sigma is greater than 0, right? So that way it is going to be a negative infinity if sigma is positive, say for example plus 2, then this is going to be e to the power minus 2t, and subsequently like that. So again, so this limit is 0 if the real part of s is greater than 0, and again here is the region of convergence for you, right? And you can verify this. So with that said, the same idea would appear here as well. You can just verify that. So the upper limit would be 0, okay? So 1 by 2j like that. So upper limit would be 0 minus 0, just like that, okay? And let me do one more thing. Instead of writing two minus signs here, let me just make one of them plus and get rid of the other. All right, instead of saying 0 plus, so 0 plus 0, if I write this and putting the upper limit here, so the point stands is that there is a condition for that. What is the condition? That the real part of s is being assumed to be greater than 0, right? And minus, if I put the lower limit here, if I put the lower limit which is 0 here, so 0 goes on top and it becomes 1. I would have 1 by minus s plus ja, sorry, 1 by minus s minus ja plus 1 by s plus ja. Again, the condition states that the real part of s will have to be 0 for this to be true, okay? All right, so again let's continue the calculation. That is, so therefore, so what we are calculating so far, we are calculating the Laplace transform of sine at. And what is the Laplace transform of sine at? We have so far seen this one, right? So let's bring this calculation here. So let's bring this to that page. So let's get rid of this. Okay, let's get this. All right, so what is the simplification here? So the answer is 1 by 2j, and of course this minus sign will appear there, so that's going to be minus here, and I would have I would have minus 1 by s minus ja plus 1 by s plus ja, and if we simplify this a bit further, 1 by 2j, and so if I just consider this minus sign to be appearing here, that's a better choice, right? So that's going to be s minus ja, s plus ja there in the denominator, and this is going to be minus s minus ja plus s minus ja, right? So s will cancel out, I would have minus 2ja. So essentially in the I have minus 1 by 2j, and here this is multiplied by, so in the denominator I have s minus ja multiplied by s plus ja, so that's going to be s square minus ja whole square, and j square is minus 1, so this is going to be s square plus s square, and in the numerator I would have s cancelling out and minus 2ja. So of course minus sign will cancel out and 2j will cancel out. I would have just a by s square plus a square, right? And of course the condition underlying the whole thing is that s, real part of s, has to be greater than 0. That is we have, therefore we have derived that the Laplace transform of sine at ut, and again, what is the purpose of this ut? Yeah, this is something someone is asking, do we have to prove this every time we need this? No, you don't have to prove this every time you need this, right? Because really in control system engineering no one is going to ask you to derive uh, the condition, derive Laplace simple Laplace transforms like this, right? No one is going to ask you this kind of things, right? But just keep in mind that every time I'm deriving something, I'm also writing the condition down, right? There is a reason for that which will be evident later on. Okay, so it is not necessary to write, for you to write down the condition under which the Laplace transform actually exists and all, right? Those conditions are kind of inherently assumed as far as the signals are causal, right? But the point is I'm writing this because I have certain things in my mind, right? So this will be very evident when we talk about stability. Let me just tell you. A stability of a continuous time linear time invariant causal system depends heavily upon, or rather rather heavily upon the region of convergence of the so-called Laplace transform. We are going to see how that actually relates to what I'm talking about here. Okay, so as such, your homework here for this particular part would be, I mean this is a very simple one. Okay, you are supposed to calculate the Laplace transform of cosine of at ut, right? And of course some of you already know the answer. That's going to be s by s square plus s square. You can also use Python to compute these things. Okay, that's not going to be anything difficult, right? So with that said, we have kind of done with our calculation. On the next class we are going to see a few properties of this Laplace transform, right? But now let's discuss our control system engineering a little bit. Okay, so let's talk about convolution. Okay, so what was convolution? The point is, yeah, about the Google Classroom thing, I'm going to provide more information on that inside Google Classroom. So you're going to get the problem. And again, yeah, you don't have to submit the homeworks anymore through email. Just don't do that. Okay, yeah, don't submit through email. Okay, all right. So I have a system here. Okay, and this system is being excited by a certain signal, input signal xt, and this signal is system is generating an output signal yt. They do not have to be causal. Okay, any system, not necessarily causal. So just to mention, not necessarily, not not necessarily causal. That's any generic system. So conditions are the conditions that we imposed on this in the original discussion here. So this is a continuous time, linear time invariant, causal, linear time invariant, single input, single output system. Okay, so continuous time, linear time invariant, single input, single output system. There are so many acronyms in this entire course. Okay, and this system has an impulse response of GT. Recall we used to consider the impulse response of systems to be HT in our signals and systems classes, and that's kind of a norm in signal processing. But in control system engineering, it's a pretty much a norm to consider the impulse response of systems to be GT. Okay. Point being, what is GT? GT. So what is impulse response? So GT is the impulse response. But what is it? So that is, what is the impulse response? That is when the input is the unit impulse signal, then the output is GT. So what is the impulse response? The response of a system when the input is an impulse signal, right? So we discussed this in our control system, in our signals and systems classes. But the point being, if I excite the system with an impulse, the output is the impulse response. And I told you, for a linear time invariant system, having knowledge of the impulse response is sufficient entirely to describe the whole system. The whole property of the system is actually can be seen from the impulse response of the system, rather for the most part. Alright, so I gave you the example of a violin being played in a hallway, right? So the example, I am not going to show you it again once again. The example was simple, that I am playing a violin in a standard room, right? It will sound like something. But what if I want to imitate the violin being played in a hallway, right? But what if I don't have a hallway? So what I can do, I can collect the impulse response of the hallway. So I can excite the hallway with an impulse sound. What is an impulse sound? Maybe something like a gunshot. So I can do a gunshot in a hallway and record the sound. So that will be the impulse response of the hallway. And then I can do a convolution between the between a violin being played in a regular room and the sound of a gunshot in that hallway, right? And if I do the convolution, the output will be output will appear to be the violin being played, appear like the violin being played in that hallway, right? Something like that. So we have seen that in our discussion on convolution earlier in signals and systems, right? So, and we also derived this. I gave you the derivation like that. So if I know the impulse response of a system, okay, and then so GT is the impulse response of a system, and if we know the impulse response of the system, then we can calculate the output of the system to any arbitrary input by doing a convolution with the impulse response of the system and the input signal. So this is the input signal. So this is the input. This is the impulse response. And this is the output of the system. So if I know the impulse response of a system, then I can calculate the output of the system with respect to any input. Okay, when we excited with any possible input, and we can calculate that through this computation known as the convolution, linear convolution rather. Okay, and of course the conditions are continuous time, linear time invariant, single input, single output. Again, we are assuming those conditions to simplify. Some of those conditions are not really necessary. Linear time invariant is necessary. The other conditions are not really necessary. So this happens for LTI systems. Okay. The other conditions are not really necessary. Okay. So with that said, the convolution integral, the convolution yt, which is this is actually given by this integration. Okay. Right? Tau is a dummy variable. So I gave you a proof of this, a very simple intuitive proof of this in one of our earlier discussions, right? I gave you a intuitive proof of this. So this can be intuitively proved by looking at certain properties of the unit impulse signal, right? And also using the linear time invariance property. That's not the point here. The point here is that what if I take a Laplace transform on the whole thing? What if I want to calculate the Laplace transform on the whole thing? So what if I want to calculate ys? What is ys? Ys is the Laplace transform of yt, right? And what is yt? Yt is the convolution of gt with the input xt, right? And what is that? That's this integration g tau x t minus tau d tau, right? And what is the Laplace transform? Laplace transform is this integration. Okay, and here is the signal, but what is the signal? The signal is this one. Hold on. See, all right. So that's the Laplace transform of the output. Wow, pretty nasty, right? Okay, but it's not very difficult to actually figure out what we can do with this. Okay, I'm going to show what we can actually do with this. And again, don't be afraid of double integrals. Okay, don't be afraid of double integrals. Let me color code a few things. Let me color code a few things so that you actually get to see what I'm going to talk about here. So this integration belongs to this limit, and this integration belongs to this limit. Sorry, this variable, right? All right, right. Now, while doing this kind of double integrals, there is something called we can exchange the integrals, right? We can exchange the integrals, so we call it the changing the order of integration, right? Changing the order of integration. So here, integration with respect to t, with respect to tau is happening first. So this inner integration is happening first, and then we have to integrate with respect to t. But under certain conditions, under certain well-behaved functions, and truly I cannot discuss this in this course. I could do this if I was teaching mathematics here, but the point is, under certain conditions, under certain well-behaved functions, the order in which we are actually integrating the signals can be interchanged. All right, can be interchanged. So before I actually do that, let me just write it down once more. So of course I'm keeping that inside. It doesn't matter because that could be a constant, that could be a variable. It will be treated as what they are. Now I'm doing a change in order of the integration. So this can be done under certain suitable conditions, right? And I'm kind of assuming that condition is being satisfied, but I cannot really teach you that, unfortunately. That would require a whole 2-hour class discussion on double integrations. So what I'm doing, reverting the order of, rather exchanging the order of integration here. See, you will see what I'm talking about. See, we have just changed the order in which the integrations were taking place. So the green integral was actually taking place first, So now this is going to be taking place later on, and the blue was going to take place later on. Now it is going to take place first. So that is something we have just done. So a very simple thing, not very difficult to understand, right? But what you need to take away from this is that as long as this green integral, this blue one is concerned, so this for this inner one, okay, for the inner integral here, okay, integration with respect to t, right? This green, this blue integral here, right? The blue one, for the blue one, which is with respect to t, this gt is going to be a constant, right? Because if I'm doing integration with respect to t, so g tau is a constant, right? Because it's a function of tau, not a function of time, not a function of t. And as such, when I'm doing this blue integral here, this can go outside, this term can actually go outside, right? Because with respect to t, this is going to be a constant, right? Because it's a function of tau and integration is being done with respect to t. So what I can write is something like this. Happy? So we can actually do that, right? Again, if you have any query, feel free to ask. All right, we are doing mathematics essentially. Again, I told you earlier, I'm telling you again, if you don't understand mathematics, you'd be kind of a crippled engineer. All right, now let's think about this integration for a moment. Let's think about this one for a moment. So whatever appears within the brackets here, and let's think about that. So I'm doing it externally, right? Let's do that externally. Let's think about that. Let's bring it here. Let's think about that small portion here, right? This blue one here. All right. So for that integral, let's do a substitution. Let's do a substitution. What kind of substitution am I going to do? I'm going to assume t minus tau to be equal to, say, for example, who knows, t minus tau could be lambda. Fine, lambda, right? Let's use Greek letters. Running out of English alphabet, Latin letters, right? So tau is a constant because integration is being done with respect to t. All right. So again, dt is going to be d lambda. And what about the limits? T and lambda. When t is minus infinity, since tau is a finite constant, lambda is going to be, so when t is minus infinity, lambda is also going to be minus infinity. And when t is positive infinity, same thing is going to happen to lambda, because tau is just a finite number, right? Right? All right. So with that assumption, if we assume that, then what can we write? This is integration from minus infinity to infinity. Okay. On this, what do I have? Instead of xt minus tau, I'm writing x lambda. Okay. And on this one, I'm writing e to the power minus s. Also, s is a constant with respect to t, right? And instead of t, so again here, t is just equal to lambda plus tau, right? So here I'm writing lambda plus tau, and dt is just d lambda. Okay, t is lambda plus, just like that. All right. So this is integration from minus infinity to plus infinity on x lambda e to the power minus s lambda into e to the power minus s tau d lambda. Now this integration is happening with respect to lambda, right? So this is going to be a constant. right? Since this integration is happening with respect to lambda, this part is going to be a constant that can go outside. It can become e to the power minus s tau, and then the integration, and we have x lambda e to the power minus s lambda d lambda. But what is lambda? Lambda is just a dummy variable, just a name, right? Lambda is just a name, right? Right? So we can do a trivial substitution. We can do a trivial substitution since lambda is just a name, right? We can do a trivial substitution and substitute lambda by t, right? So instead of writing lambda, we can write t, because this is sort of a definite integral. So the limits will be placed in this for lambda, and subsequently lambda will no longer exist. Similarly, instead of lambda, if I just write t, same thing will happen. So what I am doing a trivial substitution. So instead of writing lambda, I am writing t. That can be done, right? So what I essentially have is xt e to the power minus st dt, right? Just a trivial substitution. But what is this? One more thing. I like to be very precise. All right. But what is this? What is this? So I have e to the power minus s tau there. And what is this? What is the blue integral? This is nothing but the Laplace transform of xt. That's just xs, right? All right. So we have e to the power minus s tau xs as the blue integral. So let's go back to the original discussion here. So I was going to write this. So this one is the green one. So minus infinity to plus infinity, the g tau, and this integration within the parentheses actually turns out to be e to the power minus s tau into xs. So that's going to be e to the power minus s tau into xs. Right? Someone is asking anything? Yeah, that's the bilateral Laplace transform. All right. All right. So of course xs can go outside now, right? Xs can go outside because that's just a constant. That's just a constant with respect to tau at least, right? So integration is happening with respect to tau, so xs is a constant, so it can go outside. And I am left with this integration, minus infinity to infinity, the same thing, g tau e to the power minus s tau d tau. But what is this integral again? Okay, question is, what is this integral again? What is this one? Of course, I can again do a trivial substitution, and instead of tau I can write t. So this is going to be gt e to the power minus st dt, integration from minus infinity to plus infinity. That's nothing but the Laplace transform of gt, right? So with that said, this is going to be xs gs, right? So what we have derived is that the Laplace transform of the output of the system is a product of the Laplace transform of the Laplace transform of the impulse response of the system and the input of the system. So let's go back and copy paste a bit. So this was our discussion. So we had a system there just like that, okay, for which the input was xt, the output was yt, and we could calculate the output of the system yt but just by calculating the convolution between the impulse response of the system and the input of the system. But if we take Laplace transform on both sides, what we get is the Laplace transform of the output of the system to be equal to, so that turns out to be equal to product of the Laplace transform of the impulse response and the Laplace transform of the input, right? So this is going to be GS into just a product, simple product. All right. And you people know already that GS is now nothing but YS. GS, if I write it, GS is nothing but YS by XS. But what is this? But what is YS by XS? What is YS by XS? Right? What is that? That's nothing but the transfer function of the system, right? So this is the answer is the transfer function of the system. Right? So GS turns out to be the transfer function of the system, right? By definition. But what was GS really? I mean, we derived something. Go back to our discussion. Let's go back to our discussion. What was really GS? Oh, I can see. GS is nothing but the Laplace transform of the impulse response. Someone is asking something about the double integral, right? Let me just read your question first, because I am not getting what you are saying. When calling lambda as S. Okay, no. Someone is saying like that. I'm not calling lambda as S. Well, look very carefully. I'm not calling lambda as S. Did I write lambda as S? No. I just did a trivial substitution by writing lambda equal to T, not lambda as S. That wasn't the substitution. Lambda was equal to T. And the point being, these integrals can be done independently. So this integration is kind of independent of what is happening outside. So that was the point, right? If you're asking something other than that, you can ask me later on. All right. But what is GS? So this is this is the transfer function. What is YS by XS? This is the transfer function of the system. But what is GS? Question is, but what is GS? We just moments ago figured out. I mean, we started this as GS is the Laplace transform of the impulse response of the system. So what do we really see? We see that eventually what we come up with, we are seeing that the impulse response of the system is the transfer function of the system. So we now have another definition for the transfer function of a system, right? So we can say, for a continuous time causal linear time invariant seesaw system, the transfer function is the Laplace transform of the impulse response of the system. of the system. There is just one small point to note, is that under zero initial conditions. And why did that actually go? That zero initial condition thing actually went into this definition here, right? Okay, someone is asking about the substitution. Let me just read the question what you are writing here. No, the point being, someone is asking, okay, I understand your question, I understand your query. So if I'm doing this substitution and writing it as t, then is it not affecting the integration, this green integration here? No, it is not affecting any of those integration, because t is just a dummy variable, right? T is just a dummy variable. And maybe, just not to confuse you people, okay, you could just have written this without any trivial substitution, because that's the definition of Laplace transform. It does not matter what name of variable I'm choosing. Just not even do a trivial substitution. Let's just write it down like that, right? I think that would clear up the confusion that you might have. All right. So we have now received another definition for the transfer function of the system, right? And we figured out that the transfer function is essentially the Laplace transform of the impulse response of the system. But if you recall, I don't know whether you can recall, okay, again, if you have any query, but recall that the Fourier transform of the impulse response was also something. Recall that the Fourier transform of the impulse response of a system was called the frequency response function, if you recall. That happened in our signals and systems classes. Okay, so if I have the impulse, so basically what we have, so if gt is the impulse response, then taking a Laplace transform of this would give me the transfer function, and taking a Fourier transform on this, if possible, taking a Fourier transform on this would give me the frequency response. So this is called the transfer function, and this is the frequency response. All right, and I'm going to explain these things later on, but keeping in mind that the frequency response and the transfer function are heavily related. Okay, the frequency response of a system and the transfer function of the system is heavily related, because they are just some integral transforms which are again heavily related, right? So Laplace transform of the impulse response is the transfer function, Fourier transform of the impulse response is the frequency response. But again, Laplace transform is nothing but the Fourier transform of the signal, where I'm multiplying a decaying factor with the signal, right? So they are also heavily related. So Laplace transform, Fourier transform, they are heavily related. Okay, and they are calculating the Laplace transform and the Fourier transform respectively of the same signal. So these two are going to be heavily related. So the transfer function and the frequency response are going to be heavily related. So much so that we'd be able to just calculate the frequency response by doing a trivial substitution there as well. Okay, we shall see those things later on. But this is kind of the end of today's discussion. If you have any query, feel free to ask. Okay, and from the next class we are going to jump into certain properties of Laplace transform, because we are going to need those properties. We're going to need to understand those properties of Laplace transform, and then I think I would need 2 more classes, I think, on Laplace transform to complete the discussion. So by next week, by the end of next week, we shall have a completed discussion on Laplace transform. and then we shall go back to discussing stability of linear time invariant systems. All right, so if you have any query, feel free to ask. We went through all of quite a lot. I would suggest you read the handouts, okay, and if you find out that there are certain queries, you can ask me. Okay, all right, so that will be today's that will be the end of today's discussion. Right, I'd be waiting here for just one more minute. If you have any query, just feel free to ask. Otherwise, you can drop me an email. Again, we are going to do all the doubt clearing through Google Classroom later on. All right, thank you very much. Thank you for being here. So this will be the end of today's discussion. Thank you very much. So I'll see you next week.